In the previous video, we started off the amazing book of active inference and learned that perception can be defined as an act of inference. Namely, given some observation from the world, what is the most likely cause of those observations? Interestingly, this lies heavily on Bayes' rule. In this video, we read about Bayes' rule and understand it through a numeric example. Let's get started. Hello everyone and welcome to ML Done. Let's just continue with reading this amazing book, the Book of Active Inference. Now we stopped at a very exciting part of the book where we're actually going to get more comfortable with Bayes' rule through a numeric example. So let's just continue where we left off. We said that perception can be defined as inferring the most likely cause behind our observations. And that most likely cause can be defined as a probability distribution, namely a posterior probability distribution. And posterior means that the probability of the hidden cause after having seen the observations, hence the word posterior, right? So, Bayesian inference is a broad topic that arises in disciplines like statistics, machine learning, and computational neuroscience. A full treatment of the associated topics is beyond the scope of this book, but there are excellent resources available for those who wish to understand it in depth. However, all of this is based on one simple rule. To illustrate this rule, we consider an example of Bayesian perceptual inference. So this is the kind of inference that we were talking about, right? So for perception, we are defining perception as an act of inference. Now, we're going to see through Bayes' rule what it actually means. It's a very nice example, actually. Figure 2.1. Okay, I'm going to show you figure 2.1 in a second, just before we go to figure 2.1. Let's just understand these few lines. They are important. Imagine a person who has a strong belief that she is confronted with an apple. This belief corresponds to a prior probability, or prior for short. This prior comprises the probability attributed to the apple hypothesis and the probability assigned to alternative hypotheses. In this example, our alternative hypothesis is that it is not an apple but a frog, right? Now, the reason this is called a prior probability is because before this person, this human, let's call her, I don't know, Anna. Before Anna observes any data, she has a prior probability about how likely is it for her to be confronted by an apple versus how likely it is for her to be confronted by something that is not apple. In this case, for simplicity, the opposite hypothesis of an apple is a frog, right? So the prior probability of being confronted by a frog without having seen any data. That's why it's called the prior probability. Remember, this is a key word. Numerically, the prior probability distribution assigns 0.9 to apple and 0.1 to frog. It means that without seeing anything, without observing any data, by default, I'm just thinking that, okay, the chances of being confronted by an apple is 90%, and the chances of being confronted by a frog is 0.1, right? So these are the only two possibilities in this example. That is why the summation, as you've noticed, is 1, right? Those are the only two possibilities in this example. Note that as we have assumed that there are only two plausible, mutually exclusive hypotheses, they must sum to 1, exactly what I said. The person is also equipped with a likelihood model. This is another key word that you need to get comfortable with, a likelihood. Now, what's the likelihood? It assigns a high probability to the fact that frogs jump, whereas apples do not. Okay, so the hidden variable that I'm trying to infer, according to Bayes' rule, is going to be frog versus apple, whereas my observation is going to be whatever is in front of me, whatever the hidden variable is, am I going to be observing that thing jumping or not jumping, right? So observation and then hidden variable, or the thing that we want to infer and model perception through it, okay? So it says that which assigns a high probability to the fact that frogs jump, whereas apples do not. So why is it called a likelihood? It means that if the thing that I'm confronted with is a frog, the likelihood of observing the act of jump is high. Whereas if the thing that is in front of me is actually an apple, the likelihood of observing that thing actually jumping is very low, right? So it's a conditional probability whenever you're talking about likelihood. It means given, conditioned that my hidden variable is frog or apple, I can assign a likelihood to the observation of jumping or not jumping. Okay, so it's a conditional probability. Again, remember likelihood. So far we've learned about prior probability and also likelihood. Okay, this likelihood specifies the probabilistic mapping from the two hidden states, frog or apple, to the observations jumps or does not jump. Together, the prior and the likelihood from the person form the person's generative model. So if you combine my prior belief about the world and a model that can compute the likelihood of different observations given those hidden variables, right? These two together constitute something that is called a generative model. You're going to hear this a lot again. Okay, we're going to get more comfortable as to why it's called a generative model. In short, these two together would sort of model how me, the observer, the human, how I believe that my observations have been generated from whatever the generative process is out there that is generating these observations. Okay, how I believe for them to have been generated. Okay, but we're gonna get more comfortable with it. So if it's a little bit confusing, no worries. Just remember these two together create something that is called a generative model. Now imagine that the person observes that her apple frog jumps. Now, Bayes' rule tells us how to form a posterior belief from the prior, taking into account the likelihood of jumping. This rule is expressed as follows. Okay, so this is Bayes' rule, right? So x is the hidden variable and y is the observation. Now, this is my prior probability, the probability of x. This is my likelihood, the probability of a certain observation y given the hidden variable. This in the denominator is also called the evidence, the probability of data. And this is the tricky bit to actually compute. We're going to get back to this. This is going to bestow us with some nasty curses in the future. And this thing on the left-hand side is called a posterior probability, probability of hidden variable given observation. So if I'm observing the observation of jump, how likely is it that the thing that has confronted me is a frog or an apple, right? The hidden variable. So these two together in the denominator, the likelihood and prior, is the generative model, right? This together. And through Bayes' rule, if you notice, the likelihood is y given x, right? Through this multiplication and division, we obtain x given y. So it's like literally reversed, right? Through Bayes' rule, we can invert our generative model. So the generative model that goes from x all the way to y can be inverted into probability of x given y, the posterior probability. Okay? Now, this inversion is the act of inference, the act of perception, right? This is how we can actually infer the most likely explanation x given my observation. How the probability of the thing being a frog versus being an apple. Okay? Now, before I continue reading this, I just want to look at this figure. This is actually showing everything that we talked about right off the bat. The prior probability here, so prior probability of x being a frog in this example is 0.1, and observing an apple apparently is far more likely, 0.9. Okay? And also we have this likelihood model for apples or frogs, right? And also for each one of them, we should be able to compute the likelihood of jumps versus not jumps, right? So in this example, if you're an apple, the probability of seeing jumps is 0.01, and the other side would be 0.99, which is if you're an apple, observing the act of doesn't jump is 0.99. right? By the same logic, like if you're a frog, for me to see you jump is quite very likely. That would be the right word, right? It's likely. The likelihood is high. Versus the other way would be 1 minus that, which would be 0.19, which is if you're a frog, the probability of seeing doesn't jump is rather low, right? The most important thing is through Bayes' rule, you have your likelihood model, you have your prior beliefs, you can invert your generative model and generate the posterior probability after having seen a particular observation, right? So if you observe jumps, the posterior probability of X being a frog, versus if you observe jumps, the posterior probability of U or the hidden variable being an apple. As you see here, because we've seen jump being a frog is far more likely, like it's far more probable compared to if you're seeing a jump, but the thing being an apple. So under the likelihood model in figure 2.1, the posterior probability assigned to the frog is 0.9 and the probability assigned to the apple is 0.1. This is where I'm going to stop. I'm going to work out this example for you, okay? So I just want you to get fully comfortable with this idea. What we're interested to know is that if I'm observing jumping, right? What's the probability of, let's say, the thing being a frog, right? I just want to show you how 0.9 is computed. So I should be able to get 0.9 through inverting the generative model, yeah? Probability of X being a frog, right? So the hidden variable being a frog, if my observation is, for sure, I'm just going to put jumps. Or maybe let me just write it, just to keep the terms consistent. So this is what I want to compute, right? So according to Bayes' rule, this is equal to, first, the likelihood. The likelihood says the probability of actually observing jumps, right? Given that X is equal to frog. So in other words, if you were a frog, how likely is it for me to observe what I'm observing, which is jumps? Multiplied by my prior probability, right? So the probability of my hidden variable X being a frog. And then finally, evidence, which is the probability of Y equal jumps. So I'm gonna compute first this guy, right? The likelihood. So we are given that information, right? So if you're a frog over here, the likelihood of jumps is 0.81, isn't it? Right? So we already know that is 0.81. Now, next one is the prior probability of the thing being a frog, right? Which is 0.1, as you can see here. My prior probability, which is this guy, number 2. Okay. Now, the tricky bit is number 3. Remember this guy, the evidence. This is gonna give us a lot of trouble in the future, by the way. Now, the probability of Y being jumps, if you think about it, it consists of 2 separate terms. So the probability of Y equal jumps, you should be able to first compute. You have to consider all possibilities for the hidden variable. In other words, you need to consider all possibilities of X and marginalize that out. So in other words, 3 can be described as the summation of the joint probability of Y being jumps, right? And X, right? And this summation is over all X's, right? So X is over here. Remember, X can be only either frog or apple. So this joint probability, how can I expand this? So this would be equal to probability of Y being jumps given, so one possibility of X is being a frog, multiplied by probability of X being a frog. So that is how you can expand the joint distribution, right? The conditional and then the prior on the side. So that would be the first term for when x is frog, plus the probability of y equals jumps if x is apple, multiplied by probability of x being an apple. So this is how you can compute this. The probability of this guy is jumps versus frog, we've already seen it, is 0.81. Probability of frog, the prior probability of frog is 0.1. The probability of the likelihood of jumps if you're an apple. Jumps if you're an apple is 0.01, and likelihood of you being an apple, you can just easily compute that, 1 minus 0.1 basically, right? So that would be 0.9. Now, if you compute this, this would be what? 0.81. That'd be the multiplication of these two, and then plus 0.009, right? And then if you sum these together, you get... Okay, so this is my evidence. Okay, so now we have evidence, we have the likelihood, and we have the prior. So if we multiply 1 and 2 together and divide it by 3, we should be able to get the posterior probability, okay, according to Bayes' rule. So let's just see if it works out. So 0.81 times 0.1 divided by my evidence, 0.09. I'm worried. I hope that this will work. I'm not sure if it's going to work. Okay, so this would be 0.081. Fingers crossed. Looks good. And I can just, simplify this. This could be like 81 divided by 90. And then divided by 9, 10, and voila, exactly. So that is my posterior probability, 0.9. Okay, so before I continue with this, I just want you to get comfortable with the idea. The probability of the hidden variable being frog, if I'm observing the active jumps, is calculated through this likelihood. Is basically says that, let's say you were a frog, how likely is it to see this observation right now, or to receive this observation? Multiplied by, in general, what I think the probability of observing a frog is in the first place, right? Before even involving y, divided by what is the probability of I see anything jumping in the first place. Anything. Remember, I'm not specifying frogs, apples, tigers, nothing else. Just the act of jumping. And that is why computing this evidence is very tricky, because you need to marginalize out all possibilities for the hidden variables. That is why it's going to give us a lot of trouble in the future. So 1 and 2, we have been given that through the example. These are given data. But for 3, we said that, okay, in order to marginalize out all the hidden variables, we need to basically compute the joint probability of my observation jumps and all possibilities of the hidden variable. And this joint is basically computed through x being a frog, which is, okay, the joint probability of jumps and frog can be broken down into these two terms, right? And then the joint probability of y jumps and x being an apple can be written as these two terms. If it's confusing, just pause the video and convince yourself that these terms indeed, if you sum them together, they become the probability of y being jumps, in other words, the evidence. And then you multiply and sum, and this become my evidence, and then just following Bayes' rule, I am inverting my generative model, which is the nominator. I'm inverting them to have x given frog given my observation. Now, what I need to tell you here is very interesting. The prior probability of or the hidden variable being a frog was quite low before observing any data. And after we observed jump, you can see that there is a big shift in the probability of the thing that is in front of me being a frog, because I've seen the observation of jump, right? So that is the key important part, that when you observe a data, you tune your belief about the world, right? And this is key. This is a key concept in understanding active inference. It is through the observations that we tune our beliefs about the world, and we begin to learn about the world around us. We're going to get back to this in the future, but just remember, it is the observation that is the key. Now you have gotten comfortable with Bayes' rule through a numeric example, right? In the next video, we're going to learn about the concept of surprise and why it really matters when it comes to active inference and the free energy principle. Thank you very much.